All right, so 1.3 is called Computation of Limits. So what we've done so far with the limits in the last section is we looked at this numerical approach, this idea of getting very, very close with the table on the calculator and values, right? We also looked at a graphical approach, looking at the picture and seeing what's happening as we're moving along the graph. This is going to take more of an algebraic approach, all right? So there's some basic concepts of limits that you need to know first. And I can justify a few of these as we go with some pictures to sort of talk about them. The first one says that if you have the limit of a constant c, okay, so c is just some number, then as you get approach the value of any x value, that you're still at the same constant value. And you guys know what a picture of a constant value looks like. I'll draw it in green. This would be a constant y value of, say, something like 4 or something like that. Well, I don't care what x value I get close to, I'm always at the same y value of 4. Doesn't much matter, right? That's what that limit is saying. That limit is saying that if you're at a constant y value, well, that's the limit then. The next one says the limit, if you've got the value x of a, is simply replacing that x with the value a. All right, so from a picture point of view for that, that is the line y equal x, because that's my function right here, is the function simply x. And everywhere along that curve, if you're getting close to an x value of 5, you're at a y value of 5, the same thing, right? So along the curve y equal x, no matter what the x value is you're at the same y value. So that's the limit. All right, those are the basic ones. After that, they get a little more interesting, but they're everything that we would want to be true are true. So we've got a limit of f of x as x approaches a, and we've got a limit of g of x as x approaches a, and c is a constant. So here's the first one. The first one says that if you have a constant times your function, you could ignore the constant and just take the limit of the function and then multiply the constant when you're done. Okay? That's what we would want to be true, and it is. The next one here says that if I have two functions that are added together or subtracted from one another and I want their limit, I could find their limit separately first and then do the addition and subtraction. Everything I want to be true is. The third one's multiplication. It says if I multiply two functions together and I want to take their limit, I could just take their individual limits and then multiply those results. That's what I want to be true, and it is. I can do it in pieces and then multiply the results. The last one says that if I do the division of two functions and want that limit, I could take their individual limits first and do the division second. And that's a really good feature. It has one problem, or potential problem, is that I can't have the limit of g of x be 0 and make that work. Right? I can't have that 0 in the denominator. That's not going to be okay. So as long as I don't have 0 for the limit of g of x, I can use that feature as well. I know this slide has a fair bit of writing, so as you're finishing it, just look up at me so that I know that when everybody's done before I move on. Is anyone still writing? Okay. Are we good? Everybody good? All right. In practical application, all of those features actually give us the ability to say that most of the time we can simply take the value that we're concerned with and plug it in place of x. That's what those limit properties actually allow us to do. So if I do that on this first one, I can take this and I can plug in the number 1 in for the x. I add this together, and what do I get? I actually get 0 on that one, don't I? Be careful on where the negative is located. It's actually not located inside the square. All right, so if I plug in x equal to 1, I get a limit of this as 0. Okay. Next one, well, I can try that again, right? I can say, okay, well, we'll just try plugging in the number -3. What is 2 times -3 minus 3? -9. -3 plus 5? 2. And if you want, you can write that as -4.5, but I'm happy with -9/2 just fine, so I'm good with stopping there. What do you think? No tables, no graphs? Sigh of relief, right? Okay, we'll do the last one in this section before we stop. The last one's a little bit different, though, because this is a piecewise function, so there are different pieces to this. The other thing that's interesting on this one is that the limit is actually showing you've got x approaches 1 from the left, doesn't it? Sorry, there's no negative on your street sheet, is there? Okay, that's what I thought. Didn't remember that being there. All right, so ignore that. That's not supposed to be there. Okay. This says x approaches 1. All right? Now, we talked about in the last section, however, that if you do a limit, you're actually doing it from both sides. Well, there's no problem when there's not multiple sides of things. But once you get to piecewise functions, there are multiple sides of what's going on. Right? So we actually have to look at what happens as x approaches 1 from the left of our function. And we have to look at what happens as x approaches 1 from the right of our function. All right, so x approaches 1 is the last 2 lines of this function, right? Because that responds or is around this x value of 1 here and the x value of 1 right here. So if I'm going with x equals 1 from the left, which line of this function am I on? Here, we'll call this, I'll label them. This is line 1, line 2, and line 3. Which line of the function am I on if I'm approaching x equals 1 from the left? 1 and 2. And if I'm really close, I'm on line 2. Right in here, I have values that are close to x equal 1, but slightly smaller, right? So this says that my function value there is the number 3. I mean, that's the y value, right? It just is, it's the constant. It's the basic limit number 1 that we just did a minute ago. And then the second one says that I'm supposed to be x approaching 1 from the right. And what line am I on if I'm going to do that? That's the third line, because I'm supposed to be slightly bigger than x equal 1, and that's what this piece right here says, right? X is greater than 1. So how will I find the limit in that location? You can plug it in, just like I did on examples 1 and 2. So I can take 2 times the number 1. I don't have to put a 1 plus in. It is 1 that we're getting close to. We're just trying to figure out which piece of the equation we're using when we're looking at the one-sided limits. And if I add this together, what do I get? 3. So on this particular function, the limit as x approaches 1, which is what I was supposed to be finding, is 3. But you have to show me both one-sided limits to actually verify that, right? That wouldn't have had to happen. If this instead of said 2x plus 2, this limit would all of a sudden not exist. Everybody good? All right.